Hello everyone, my name is Ava and I will be presenting a formal model of concurrent planning and execution with action costs. In recent years, big progress has been made in solving both classical planning problems and temporal planning problems. But most planners still make the naive assumption that time does not pass while they are planning. This assumption can be unrealistic, especially in domains that contain external timing constraints, such as deadlines. For example, consider an agent that needs to get to the airport and can do so by taking a taxi or by taking a bus. We can think about these two options as partial plans that need to be elaborated into complete plans. Then clearly, the agent should elaborate the bus plan only if it can be elaborated into a complete plan before the bus leaves. So situated temporal planning is a model that tries to handle that problem. Situated temporal planning is a model for the planning problem faced by an agent for which significant time passes as it plans. In this setting, external temporal constraints are introduced depending on the actions in the plan. For example, the action taking the 9 o'clock bus introduces a new constraint that the agent must be at the bus stop by 9 o'clock. But all these works still assume that the planning process must terminate before starting to act. In some cases, this might be problematic since planning takes time. We might miss good valid plans that become invalid as time passes. So we now formalize our model. We start with an example and then we will see how we can translate this example into an input of our model. So again, consider an agent that needs to get to the airport. And suppose that it can do so by riding the train or by taking a taxi. The agent needs to be in Terminal A at the airport in 30 minutes from now, otherwise it loses $500, which is the cost of the flight. We call this $500 the cost of failure. This is the cost that the agent pays in case it fails to find a plane on time. We assume that the train leaves in 8 minutes, the ride lasts 20 minutes, and the cost is $5. The taxi arrives in 5 minutes from the moment it is ordered. The ride lasts 18 minutes, and the cost is $30. We assume also that the agent has already found that the first action in the train plan is walk to the train station, which requires 5 minutes. The second action is ride the train, which requires 20 minutes. But the agent has yet found what to do at the end of the ride. It may require an additional 10 minutes to walk to Terminal A. We say it with probability 0.2. Or Terminal A might be adjacent to the train station, which requires no additional actions, with probability 0.8. The agent also found that the first action in the taxi plan is call a taxi, which requires 1 minute. The second action is wait for a taxi, which requires 5 minutes. And the third action is take the taxi, which requires 18 minutes, as we already mentioned. But again, the agent has yet found what to do at the end of the ride. We know that at the end of the ride, there is a payment, which requires 2 minutes with probability 1. Finally, we assume that the time required to find the rest of the train plan is 2 minutes or 7 minutes, each with probability 0.5, and the time required to find the rest of the taxi plan is 4 minutes with probability 1. So this is the example. Now we see the formal definition of our model. In our model, we assume that the environment is deterministic and fully observable. The only uncertainty that we have is regarding the process of planning itself. So how long it will take to plan, how long it will take to execute the plan, and what is the cost of the plan. Our model is called COPEC for Concurrent Planning and Execution of Action with Costs, and it extends the AC squared model proposed by Shperberg et al. To allow for concurrent planning and execution. In our model, we assume that we have n computational processes that all try to solve the same problem. We can think of those processes as partial plans that are competing to be elaborated into complete plans. So in the example we saw, we had two processes, one that represents the train plan and one that represents the taxi plan. We also have a cost of failure which is the cost that we pay in case we don't find a plan on time. In the example, it was the $500. And we have a set of base level actions denoted by B. These are the actions that we can execute in the real world. So for example, the action walking to the train station. And we assume that each base level action has a fixed duration. We also assume that each process has already computed a prefix of its complete plan, and we denote it by HI. And a process I can compute the rest of its plan, denoted beta I, when given enough computation time. We assume that we are given a number of distributions. First, MI, which is a distribution over the time required by process I to find a solution. CI, a distribution over solution cost for process I. XI, a distribution over the deadline for process I. And RI, a distribution over the duration of the remainder of the plan found by process I. And the objective of the COPEC model is to find a policy for allocating computation time among the N processes and executing base level actions, as well as optionally stopping and executing a complete plan so as to minimize the expected cost of the executed plan. So now that we have our model, we can go back to the example and see how it is translated into a COPEC instance. So like we said, we have two partial plans, one for the train and one for the taxi. And so this is the translation into a COPEC instance. We have the set of base level actions, which is walking to the train station, calling a taxi, waiting for the taxi, riding the train, and taking the taxi. We have the duration of each base level action as given in the example. So the duration of the action wait for a taxi is 5. The cost of failure is 500, like we already said. And we have two processes, process one that represents the train plan and process two that represents the taxi plan. We said that the agent already found the first two actions in the train plan, which are walking to the train station and taking the train. So that represents the prefix H1. We said also that finding the rest of the train plan requires 2 minutes or 7 minutes, each with probability 0.5. So this represents the M1 distribution. We said that the cost of the train is 5 with probability 1. So this is the distribution C1, the distribution over the cost of the plan. The deadline is 30 with probability 1. So this is the distribution over the deadline. And the time required to execute the rest of the train plan is 0 minutes with probability 0.8. This is in case terminal A is adjacent to the train station, or 10 minutes with probability 0.2. This is in case the agent has to walk to terminal A. So this is the distribution R1. So now we can construct process 2 in the same way. And now that we translated the example into a COPEC instance, we can use our methods to find good policies for this example. So we will now see the main algorithm that we propose to solve the COPEC problem. It's called min-let DAG, min because we want to minimize the cost of the policy that we find, and let stands for latest execution time, which is the time at which we execute the base level actions. The algorithm makes use of the DAG algorithm proposed by Shperberg et al. To solve the AC squared model. The DAG algorithm basically gives a value to each process, and we can use that value to decide which process we want to give computation time to. So the idea of the algorithm is that for every process J, we first fix a deadline DJ by choosing a value from the support of the distribution over the deadline for process J. Then we compute a mapping function from the base level actions in the prefix HJ to the latest execution times of the actions according to the fixed deadline DJ. So for example, if the sequence HJ has only one base level action B, then the latest time to start executing action B is simply the deadline DJ minus the duration of the action B. Then given the mapping function ij, we can compute the exact time at which every process will be invalidated. We call this the effective deadline of the processes. And finally, we can compute Given the effective deadlines, we can compute a value for all the processes using the DAG algorithm that we mentioned. So then we choose the process I that has the highest value, and we either give computation time to process I or execute base level actions according to the mapping function II, which is the mapping function of process I. For the empirical evaluation, we used the weighted 15 puzzle problem. We solved 60,000 instances of the problem using A star with the weighted Manhattan distance heuristic. And for each initial H value, we created 3 histograms, one for the required number of expansions, one for the optimal solution length, and one for the optimal solution cost. And we used this histogram to create the distributions of the processes for our inputs. So to create a COPEC instance, we first drew a random weighted 15 puzzle instance. We then ran A star until the open list contained at least n nodes. And we chose the first n nodes from the open list. And these nodes represent the processes of our input, and their distributions are represented by the histograms corresponding to their H values. The base level actions in the inputs are move a tile up, down, left, or right, and we assume that they all have the same duration. So here we have some results. We solved each COPEC instance that we created 3 times, each time with a different duration of the base level actions, 1, 2, or 3. The plots presented are the average expected cost of the policy found by the algorithms divided by the cost of failure. And the x-axis is the average runtime of the algorithms in log scale. The legends are sorted by algorithm performance from best to worst algorithm. So we can see here that the best performing algorithm is the min-net DAG algorithm. The dots in the plots represent algorithms that do not execute base level actions before finding a complete plan. The squares represent demand execution algorithms, which is another COPEC scheme that we implemented. And the rest of the shapes represent the min-net DAG algorithm with different parameters. An interesting thing that we can see from the results is that as the duration of the base level actions grows, the performance of the algorithms that do not execute base level actions gets worse. So for example, here we have results for inputs with 10 processes and duration of the base level actions is 1. We can see that the non-executing algorithms perform relatively well, especially the MPP algorithm here, which is very close to the best performing algorithms. But even when the duration increases to 2, we can see that the performance of the MPP algorithm here gets much worse. And it gets even worse when the duration increases to 3. We can see the MPP algorithm here, which is much worse than before. The same goes for 20 processes and duration 3. We can see that the non-executing algorithms here perform much worse than the COPEC algorithms that we implemented. On the other hand, we can see in all the results that the COPEC schemes that we suggested perform relatively well even under severe time pressure, so even when the duration is 3. This is because they do not wait to find a complete plan to start executing actions, which allow them to find better policies. So to conclude, in this work, we extended the AC squared model proposed by Shperberg et al. To allow for concurrent planning and execution. We developed greedy algorithmic schemes for the general case of the COPEC problem. And we designed experiments by generating instances from the weighted 15 puzzle problem and showed that our greedy schemes perform well. And with this list of future work, I conclude my talk. Thanks for attending this talk.